The last speaker, and just before we start, the title has to do with Gödel and Giancarlo Rota, and I have commented to Palle that I had a number of occasions to have a brief conversation with Giancarlo Rota, so I'm very interested in finding out what he said about the pernicious influence of mathematics, some advice from Gödel and Rota. So it's a pleasure to present Professor Palle Yourgrau, who's a professor of philosophy at Brandeis University.
Thank you. In effect, this talk is a commentary on Giancarlo Rota's essay, The Pernicious Influence of Mathematics on Philosophy, and also on Kurt Gödel's essay, The Modern Development of the Foundations of Mathematics from a Philosophical Perspective. I borrowed the title of Rota's essay with a slight twist, and indeed not just my title, but my very approach twists somewhat Rota's. The theme of his essay is that mathematics is perfect already in its own peculiar realm, which he describes as a realm of facts, though it might equally be described as a realm of a certain method, the deductive method, and that trouble only starts when what are called analytical philosophers, the descendants of Frege, Russell, Wittgenstein, Carnap, and Quine, derided by Rota as what he calls mathematizing philosophers, and he means that in a bad sense, apishly trying to imitate the methods, goals, and ideals of mathematics, which he says gives the appearance to genuine mathematicians of someone attempting to pay his bills with monopoly money. For Rota, the pernicious influence of mathematics is its illegitimate effect on the mathematizing philosophers. My theme, by contrast, is the pernicious effect of mathematics on thought as such, including and especially the thoughts of those very mathematicians with whom Rota finds no fault. Rota lays the blame for the pernicious effect of mathematics on philosophy solely on the mathematizing philosophers, whereas I think mathematicians themselves must share some of the blame, and not just for the effect mathematics has had on philosophy. I agree with Gödel, then, who argues in his essay that of the two fundamental philosophical worldviews, which he calls, for no reason I can fathom, the leftward direction, which inclines to skepticism, materialism, and positivism, and the rightward, which is in sympathy with metaphysics, religion, and idealism. Mathematics, though it belongs by its nature, mathematics, though it belongs by its nature on the right, according to Gödel, has moved increasingly to the left in response to the zeitgeist. Quote, mathematics, this is Gödel, by its nature as an a priori science, always has in and of itself an inclination to the right. That is toward metaphysics and theology and idealism, and for this reason has long withstood the zeitgeist. End quote. But he continues, around the turn of the 20th century, its hour struck, prompted by the antinomies of set theory, of which we've heard a lot today. Now, I cannot, though it pains me, agree with Javier when he writes in his book, Mathematics and Religion, though it's actually part of a hypothetical, so I'm not sure it's quite fair to attribute it to him, that, quote, mathematics has led the evolution of human rationality across history, end quote. He used the word if, but I'm ignoring that. Through much of history, I cannot say, but from my own very limited experience from the outside, I'm not sure that mathematics takes the lead today vis-a-vis rationality. Nor do I concur with Rota when he writes that, quote, philosophy's relationship with the goddess reason is closer to forced cohabitation than to the romantic liaison which has always existed between goddess reason and mathematics, end quote. Javier, like Rota, sees mathematics and metaphysics as complementary disciplines, whereas I believe that in an important sense they are in tension. You cannot serve two masters, says Plato. The two masters here, I suggest, are not the realms of mathematics and of metaphysics, but rather the universe of reason versus that of unreason, or mere technique, logos versus alogos. And I do not need to remind this audience that in the opening lines of the Gospel according to John, in the beginning was the Word The Word was with God, the Word was God. The word translated here as word is, of course, logos. The tension I'm speaking of is not then between competing areas of interest, nor even in modes of investigation, but rather between thoughtfulness and thoughtlessness, insofar as mathematics, I'm afraid, all too often discourages thinking. Not just thinking about metaphysics, thinking as such. To a considerable extent, I believe mathematics as it is currently practiced is bad for one's mental health. Obviously, I'm exaggerating, and I don't mean to include this audience. But actually, it's not really. It's only partly a joke. It's only partly a joke. God's mercy preserves mathematics from being drowned in mere technique, wrote the great French philosopher Simone Weil. If only this were true. Unfortunately, I believe God's mercy is still much needed in this domain. Why am I saying these things? A training in mathematics gives one all too often the illusion that mathematics is just a practice in deduction. That fits logic better than mathematics, but it's actually wrong about both mathematics and logic, as Rota himself emphasizes, and as Javier has emphasized. He attributes the misunderstanding to the, quote, mathematizing philosophers, that mathematics is just deduction, but I think all too often mathematics itself, judging from my many students who come to me straight from their mathematics classes in Brandeis, it encourages this mistake. I hear this all the time from my students. Mathematics, that's just deduction. Again, Javier himself is quite clear as a mathematician that deduction or proof is only a part of mathematics, but deduction remains, I think, for all too many, inside and outside mathematics, the primary aspect of the field. Mathematics, thus, all too often gives the impression that all knowledge is ultimately based on proof. For Gödel, this is one of the illusions of positivism. This is false, of course, even for mathematics itself. Proof, obviously, rests on unproved, indeed unprovable, axioms and methods of proof. It is often said, I've read this many times, it is often said that Gödel proved that not everything in mathematics can be proved. We don't need Gödel to achieve this obvious insight. We will need Gödel later, but not for this. Okay. Mathematics all too often seems to project the paradigm of complete axiomatizability as in Euclid's ideal, captured in the modern concept from Frege, Hilbert, Turing, and others of a formal system. Here we do need Gödel. His famous incompleteness theorem demonstrates conclusively that that ideal, complete axiomatizability, is an illusion. Mathematics, as Plato was the first to notice, rests ultimately on non-mathematical foundations. The palace of mathematics does not rest on the foundations of a super palace, but rather on something very different from the palace itself. Hilbert attempted a compromise, hoping to prove that a safe and secure part of mathematics, what he called the finitary part, finite, that's not finite, that's a technical term, finitary, could serve as the ultimate foundation for the rest. Gödel's two incompleteness theorems shattered Hilbert's dream. Now, a little side note. As a footnote to Gödel in the leftward direction of the zeitgeist, it is noteworthy that in current debates as to whether evolution provides a complete account of all facets of human life and experience, including the sense of beauty, and listen to what Paul said earlier today and previously, it appears that the ideological purists among evolutionists, which seems to be most of them, have an almost religious conviction that there cannot possibly be more to evolution than random, undirected mutations that aid survival. Any suggestion of a filter or pattern or a higher order law of nature, not to say intelligent design, is dismissed as, quote, unscientific. Indeed, any attempt even to challenge or modify the theory of evolution is considered unscientific. To adapt a wonderful phrase from Gödel, these so-called extreme empiricists turn out to be a priorists with the sign reversed. That is to say, they appear to have an a priori belief that the empirical theory of evolution cannot in any way be modified. In particular, they have a kind of religious devotion, I'm using the word now in the negative sense, a kind of religious devotion to the idea that evolution is in the strongest sense mindless. As Gödel said, quote, Materialism is inclined to regard the world as an unordered and therefore meaningless pile of atoms, whereas theology and idealism see sense, purpose, and reason in everything, end quote. So I think Gödel's idea that the zeitgeist is moving to the left is very strong, actually, and it's really quite striking that people sort of are determined that evolution can remain mindless. Any suggestion that there's anything else, they fight fiercely. You might say, isn't it an open question? Let's look and see. They seem to have this really sort of inbuilt idea that it's really got to be meaningless. Okay, to continue. But now, back to mathematics. Rota calls mathematics a science that deals with facts, like any other science. But is mathematics just like other sciences? Let's compare. For years, biologists, having already discovered in detail the properties of the gene, the laws of heredity, tried to discover something more fundamental, to wit, what the gene itself actually is. The same with physicists and the atom, and later with black holes, and now perhaps with strings. By contrast, mathematicians, in spite of the great work of Frege, sneer at philosophers who are concerned with such questions as what numbers or sets or functions really are. Timothy Gowers, thus, writes in his little book, Mathematics, a very short introduction, his contribution to a very interesting series of brief introductory texts put out by Oxford University Press, a short introduction to blank, to X, Y, Z, to existentialism, to Judaism, to etc. So here's one is Mathematics introduction. Here's a quote from Timothy Gowers. There are certainly philosophers who take seriously the question of whether numbers exist. The main purpose of this chapter is to explain why it is that the mathematician can, and even should, happily ignore this fundamental question. He recommends not thinking. Okay, end quote. Indeed, Rota himself speaks about surreal numbers in another paper of his, A Mathematician's Gossip, and says, quote, we will wait another 50 years before philosophers get around to telling us what surreal numbers, quote, really are. So he also derides that philosophical enterprise. Amazingly, Frege, who did to the foundations of mathematics what Newton did to physics, is the patron saint of analytic, or for Rota, mathematizing philosophers, not of mathematicians. Frege's Foundations of Arithmetic, the Grundlagen, is required reading for all first-year PhD students in philosophy at MIT. I haven't checked, but I dare say there's no similar requirement for the PhD student in mathematics. It is the structures themselves that matter, one hears from mathematicians, not what's in the structures. The structures of what? If there are no numbers or sets, can there be infinite structures of numbers or sets? Can one substitute genuine material objects for numbers, say grains of sand? But are there enough grains of sand around to do the job? Should we speak rather not of actual, but of possible grains of sand? Would merely possible material objects, however, really be a metaphysical improvement over actual abstract numbers? And what are the structures themselves? Do they really exist for the mathematician, or should we only speak of structures of structures? And yet, far from attempting to answer such questions, mathematicians, as we have seen from Timothy Gowers, all too often only counsel us simply to ignore them, and to ignore the related question of whether the axioms on which theorems about structures rest are themselves actually true. Listen again to Gowers, quote, what matters about an axiom system is less the truth of the axioms than their consistency and usefulness. What a mathematical proof actually does is show that certain conclusions follow from certain premises, such as the principle of mathematical induction. The validity of those premises can safely be left to the philosophers. End quote. In Gödel's words, for such mathematicians, mathematics is no more than, quote, a mere game of symbols according to certain rules, not supported with insight, end quote. Compare Frege and Peano, whom we just heard about, on the so-called Peano postulates for number theory. Actually, it's should we put the Frege, Dedekind, Peano postulates, actually. All three had them. Frege derived them from his theory. Others postulated them. Peano, the mathematician, simply postulated his postulates, just as Gowers recommends. By contrast, Frege attempted to prove his from a small set of axioms so basic that, as the very foundation of reason itself, their truth could not be questioned. No physicist or biologist or any other respectable scientist would speak the way Gowers does about his lack of concern for the truth. Why is mathematics different? Is it a genuine science or not? Science, I think, it aims at the truth. Other things don't. Chess doesn't aim at the truth, etc. Baseball doesn't aim at the truth. Is it a genuine science or not? Frege's entire philosophy of mathematics, I suggest, consists of an attempt to put mathematics on a firm foundation as a genuine science. Everything he does follows from this one premise. Mathematical induction, for example, which Gowers simply suggests we simply accept because it seems right, or at least useful. Frege attempts to derive from more basic principles via rigorous proof. Of course, ultimately for Frege, mathematics and logic, assuming there's a difference, rests on a few basic axioms that cannot themselves be proved. How are these to be justified? Frege accepts them, in effect, as given a priori to anyone who understands mathematics and logic. Unfortunately, he has very little more to say about this, a crime for which he was punished by a just God, since his famous axiom 5 on the existence of sets, identity, was shown by Russell's paradox to reduce his entire system to logical inconsistency. There's something very tragic and ironical about Frege. By the way, the greater the logician, the more likely you'll contradict yourself, because you speak precisely. Whereas the intuitive mathematician is sufficiently vague that problems don't arise. It's not an accident that Church's theory had an inconsistency, Quine's theory had an inconsistency, and Frege's theory had an inconsistency. That's in a way a sign of how rigorous they were, that you can actually find an inconsistency in it. It's also an irony that happens to logicians, most of all. Gödel, by contrast, says explicitly that since mathematics needs in some way to justify its axioms, which cannot be proved or simply defined into existence, it must attain, quote, a clarification of meaning that does not consist in giving definitions, end quote. For assistance in this task, Gödel turned to the philosopher Edmund Husserl's phenomenology, which he thought offered hope that we could find a systematic method that would achieve a clarification of meaning by, quote, this is Gödel now, by focusing more sharply on the concepts themselves, by directing our attention onto our own acts of the use of these concepts, end quote, by internal reflection of our own activities as a mathematician. It remains unclear, however, whether in the end Gödel found that the promise of Husserl was fulfilled. I myself can get nothing out of Husserl. I've certainly tried. The challenge posed by Gödel, however, remains. If mathematics is to deserve the name of a science, then like all sciences, it must seek the truth, including the truth of its axioms. Unlike mathematicians, physicists often investigate the nature of the objects under investigation. Einstein, for example, tells us what time itself is, the fourth dimension of a special kind of space-time. What energy is, E equals mc squared. What gravity is, space-time curvature. Similarly, before Watson and Crick, much was known about the gene, except what it actually is, which is what Watson and Crick told us. If mathematicians have no interest or ability in determining what numbers, say, are, perhaps philosophers can help them out. Properly taught, I suggest, mathematics should serve as a springboard for metaphysical and theological reflections, a source, for one, among other tasks, of analogies. Consider, even a very large, finite natural number is no closer to infinity than the very smallest of numbers, just as no human being, no matter how great, is any closer to God than the least among us. That's, I think, food for thought. Even a really big number is just as far from infinity as the number 2 and 3. It's literally as close as 2 and 3. Further, which my students often find very unpleasant, but it's a very sort of strange fact. So how do people learn about infinity by considering big numbers? That's another question. Another sort of mystery. They do somehow. Further, the very existence of infinity, actual infinity, points us towards something mysterious and beautiful. Frege reaches infinity in an amazingly clear and beautiful way in the Grundlagen. The number, he says, that belongs to the concept, finite number, is an infinite number. I cannot agree, however, with Frege when he goes on to add that, quote, about the number he uses the Lemniscate, infinity, so defined, there is nothing mysterious or wonderful, end quote. That the number that numbers the natural numbers is not itself a natural number, but rather a supernatural number, is to me the very essence of something mysterious and wonderful, in just the sense in which there is something mysterious and wonderful in Cantor's proof that this supernatural, or as he calls them, transfinite numbers, this supernatural or transfinite number is only the first of an infinite series of transfinite numbers, not to mention the proof that this infinity of infinities cannot itself be numbered by any of the infinities contained therein. If these things are not wonderful, I don't know what is wonderful. By the way, just to remind you, that Cantor discovers a whole hierarchy of infinities. The smallest one, numbers, the natural numbers, that's Frege's one. Then there's Aleph 1, Aleph 2, Aleph 3, etc. Exactly what Aleph 1 is a good question. That's Cantor's continuing hypothesis. But he does prove, by the power set axiom, that every set has a bigger set, including. So there's actually an infinite hierarchy of infinities. But how big an infinity of infinities? The answer is none of the infinite numbers, the alephs, is big enough. Cantor has a name for the infinite list of infinities. He calls it God. And he says it's not mathematizable. He says math can't handle it. Okay. If that's not wonderful, I don't know what's wonderful. The significance or the actuality of actual infinity cannot be exaggerated. Actual infinity versus potential infinity. Though Cantor's great discovery remains to some extent controversial. Not for nothing does Aristotle, following Plato, declare the divine to be pure actuality. Indeed, since he identifies potentiality with materiality, Aristotle, this is one of the reasons he concludes that God, the unmoved mover, as pure actuality, cannot be material. No potential, no material. Be all you can be announces a well-known poster for the U.S. Army. You may have seen these. In fact, that's only true of God. Whatever the Army tells you, they're lying. Consider further, if a three-dimensional object, these are more analogies from mathematics, I think that should help theology. Consider further, if a three-dimensional object, say a sphere, moves through the plane of two-dimensional flatland, as in the book Flatland, what will the flatlander see? They'll see a series of circles, smaller and bigger and then smaller again. They won't see a three-dimensional sphere because it's a two-dimensional flatland. And, of course, no one can prove to them that there are such things as spheres. There may be some Moses among them hypothesize that there's a higher being. But of course you can never prove them wrong. And I think the same is true of God, no matter how he may appear in this flat world of ours. Don't look for proof. Mathematics teaches us that the invisible is real. Indeed, that the invisible realm orders or gives form to the visible. Just as Plato taught, that's one of the main themes of Plato's Phaedo, that the invisible realm not only exists, but in fact it gives order and form to the visible realm. Very unintuitive idea, you may think. Plato also taught, where there is order, there is intelligence. A very interesting idea. Frege's philosophical explorations on the foundations of the theory of numbers is also, read correctly, a valuable tool in coming to grips with theological concepts. I think I'm sort of alone in bringing together Frege and theology. Indeed, the lessons of Frege, that mathematics should proceed like a science, like any proper science, that is, as a form of systematic knowledge, seem to have been lost by mathematicians, and so an indispensable tool for grasping theological concepts has been lost. Let us begin with the number 1 and work up to 3. God is one. I think Paul just quoted this, saying God is one. We read the Bible, say the monotheistic religions. But what does this mean, that God is one? Frege in the Grundlagen emphasizes the distinction between being one in number and being unified, even though unus is a root of both. Being simple is yet a third idea. Being unified or united is a property of an object, like the United States of America. Being one in number, by contrast, is a second-order property, the property a concept has of having exactly one instance. That's Frege's philosophy. God may or may not be unified, but this is not the idea behind monotheism. Rather, the idea that there is one and only one instance Rather, the idea is that there is one and only one instance of the concept, God. So I'm claiming that you can't even understand monotheism unless you have some idea of the philosophy of arithmetic. God is one sounds like God is wise and God is good, but it's actually not such a property of God. And then people simply say God is simple. That's a different property of God. It is not really God then that is one. It is the concept of being God or being divine that has one unique instance. One cannot even grasp the basic idea of monotheism then without some understanding of the philosophy of arithmetic, which I think is not usually taught in theology schools, so I haven't actually gone to one, I suppose. Which unfortunately is taught, it seems, by philosophers, and not too many of those, not by mathematicians, even though Frege was a mathematician. Which brings us to the number 3. Now we've moved up to 3. My students at Brandeis, it's embarrassing to say this, but I have to be honest, my students at Brandeis frequently declare that Christians aren't monotheists, since they believe in the Trinity. This stopped me in my tracks the first time I heard this, and was a bit taken aback. I tried to correct their misunderstanding, gently I hope, by pointing out that no, Christians, just like Jews, are monotheists. In what sense then, for Christians, is God also 3? That's a good question. 3 isn't 1. I mean, nothing gets by my students, okay? Well, it is not that God is 3 in number, in the sense that there are 3 gods. That's not what Christians do. Then they would be polytheists if they said that. John Donne's God, from Holy Sonnet 14, consider this: "Bad in my heart, 3-person God." 3-person God, he says. "For you as yet but know, breathe, shine, and seek to mend." That God of John Donne is still one God, but a 3-person God. But these 3 persons are not parts of God, like my head, torso, and legs. Something there's this part of God, this is part of God, and this is the lower part of God. This is what is meant by God's being simple, a concept first developed by Plato, whose forms he insisted were simple. Simple is anything but a simple concept. It's actually a very tricky concept. People say God is simple, you think the number 2 is simple. God's a little more complicated than that. What do you mean? Okay. Unlike a physical object that is beautiful, say Helen of Troy, who has a beautiful nose, beautiful eyes, beautiful lips, all distinct but related. Beauty itself, this is Plato, beauty itself cannot be divided up into parts. There is no lower part of beauty distinct from the upper part. Helen's face has parts. The beauty of her face does not have parts. Plato insists on this. It is, so to speak, all beauty all the time. And the numbers themselves, says Plato, amazing he did this 2,500 years ago. The numbers themselves, says Plato, what Frege calls the counting numbers, what we call the positive integers and 0. The numbers themselves, he says, are forms, and so simple. Now you think, just a moment now, simple. Isn't it true that 3 is equal to 1 plus 1 plus 1? That's true. But does that mean 3 has 3 parts? 3 is indeed the sum of 1 plus 1 plus 1, but as Frege demonstrates, that is not to say that the number 3 has 3 parts. 3 does not, like a Russian doll, contain 3 ones inside itself. It's not pregnant with 3 little ones. What's amazing is Plato knew this 2,500 years ago before Frege and logic. He's a smart guy, Plato. But let me tell you how smart he is. He knew no more that he got from Socrates. So he knew that he knew something, but no more. And he knew he couldn't say anything more because how could he? It required logic, mathematics, in a couple of thousand years. But he knew the fact that it doesn't have parts. That's what I call a good philosopher. And Frege repeats this, though I think it doesn't quote Plato. Indeed, so 3 is not, if you want to picture 3, you don't have to draw 3 of something. That's a mistake. You don't have to, again, draw a big circle and put 3 little, if you cut out the number 3, you won't get 3 little pieces. Which means, actually, you can't picture it. No picture can do it justice. Frege also pointed out, by the way, there aren't even 3 ones in the first place. The Good Life is a very funny book, but you've got to get the jokes. Some people have actually said this. They said 3 is 1 plus 1 plus 1. But 1 is just 1. So it must be 1 sub A, 1 sub B, 1 sub C. But then you're in real trouble. So it looks like, but the 3 isn't just 1. So what's going on here? It turns out what is meant by 1 plus 1 is actually rather tricky. That was Frege's point. It doesn't mean what you think it means, at a minimum. shall we say. What is meant by 3 being the sum of 1 plus 1 plus 1 is not that it has 3 parts, but something more subtle, which Frege illuminates in the Grundlagen. If you say what, you've got to read the book. It's a complicated story. but it's not that it has 3 parts. The mathematical function of addition must be distinguished from the physical operation of heaping or agglomerating, something Plato recognized already in the Veto. Same thing Plato understood. You don't stack the numbers on top of each other like you can long pieces of wood. You stack it in that way. Indeed, Plato makes a really beautiful point. It's just amazing. He says that if you heap things, adding 1 more grain of sand changes the amount of sand very little, and yet it changes addition of 1 to a number. It makes an entirely different number. Frege made that point too. Leibniz made that point also. It's actually amazing. So that just shows that adding another is not like adding a grain of sand. It requires a whole lot of grains of sand to get a different kind of heap. Just add 1 number, you go from prime to non-prime, from even to odd, the whole thing changes. So it's a very different operation, adding 1 in numbers, than adding 1 more log, 1 more pea to your plate, 1 more grain of sand. So adding is an ambiguous word in these 2 cases. Frege knew this very well. If one understands Frege, then, one is in a position to understand that when a Christian says that God is at the same time the Father, the Son, and the Holy Ghost, he or she is not saying either that there are 3 gods or that God has 3 parts. He is saying something analogous to what the mathematician says when he announces that 3 is a sum of 1 plus 1 plus 1. Now let me be clear here, or rather unclear. I'm not saying he's saying that literally, but I'm saying it's a different process, just the way 3 is 1 plus 1 plus 1. What it means is that what you need is a Christian arithmetic. You need to understand what is meant by that. And it's not parts, and it's not having 3. It's something different. And Frege has given us a model of how you can have 3 ones and not have 3 parts, and that's in actually arithmetic. So arithmetic itself gives us the clue that one can say this without being a polytheist or believing that God has different parts. So, to conclude, in sum, mathematics, I suggest, properly appreciated, properly approached, provides a powerful springboard to assist the leaps of the theological imagination, and in the other direction, a foundation for the very concepts that lie behind the idea of God. What I, following Rota, but twisting his meaning, have called the pernicious influence of mathematics results from a distortion of the proper role of mathematics, if it would only assume its rightful place in what Gödel has called the rightward direction in philosophy, the path toward metaphysics and religion. Thank you.
Thank you very much. I have not well understood everything, but in any case, my reaction is that what mathematics is the dimension of our language, is part of our language that we have learned working on geometry first, working on geometry and arithmetic, working on geometry and arithmetic, we have discovered many things, and now we apply this to different structures we find everywhere. Then it's a language. For me, it's mainly a language. But language is very much. In this, well, now coming to some things you said, because mathematics is only a language, yes, mathematicians are they are experts in the language, but sometimes they don't reflect enough on the language they use. They are expert, but well, this is only a reaction.
Yeah, good. By the way, so to this, I must say, I'm not in agreement with you. One of the questions I pose in my paper, which Frege poses, is mathematics a science? Well, if it's a language, it's not a science. You have to choose. There is a language of mathematics. Yes. That mathematics is not, if it's a science, is not just a language. It aims at truth. language doesn't aim at truth. Language is a means of conveying it. So I think there is a language of mathematics.
Yes.
And if that's the case, then if it's a science, it's still aiming at truth like any other science. And the fact that it's a different language will not get it off the obligation to seek the truth. There's another question, which, I mean, you raised some very interesting points in your book, which take me a long time to discuss, but my inclination is always Fregean, with Frege. And so you talk about different languages and different systems, but I think ultimately, that they must be unifiable. So I think they are just different. They aren't ultimately different languages, not even ultimately different sciences. They're just one truth. We bracket it to mathematics or geometry or butterfly collecting or bomb making, but there's just different branches of the truth on this theory. And that's very much Frege's idea. Truth is truth. There's not truth in mathematics, or same with existence in mathematics. It's just existence. Yes. That's one theory. I mean, it's one approach. This approach I tend to favor. So that's a different way of looking at it. But again, people often, I think language is more, mathematics has a language, a very powerful language, which it develops and which science borrows a great deal. But mathematicians use the language of math to investigate mathematics. Physicists use the language of mathematics to investigate empirical objects. That's why a blackboard looks very similar. But it's very different. If you look at a physicist, it'll look like a mathematician, except he's not doing math. I hope he's not doing math. He's doing physics, but it's the same language.
Yes, thank you.
Yes, I was quite impressed when you spoke about the Trinity and totality, because I remember the great Trinitarian theologian, San Gregory of Nazianzus, who says explicitly, the 3 in the Trinity has no arithmetical signification, it's a meta number.
It's a meta number?
Meta number. Because it's not arithmetical, he says.
Yeah.
So you should not put a numerical signification on the 3 on the stick of the Trinity.
I guess I'm suspicious of that. I prefer my way of doing it. And first of all, 3 is a pretty mathematical word. So for instance, I mean 3 in the non-mathematical sense of 3, I'm a little mystified. Why not say Google or Shmoo or something? But in a way, on the other hand, I think the spirit of that remark I'm friendly with, because what I'm saying is they're different. It's not an ordinary use of the number 3.
Right. Yeah.
And Frege is saying, or at least it's a different application of the number 3.
Yeah, right.
But I think we can understand that use if we look at it.
His point,
Yeah.
not do arithmetic with the 3 of the
Yeah.
Trinity.
But it's interesting that monotheism uses the word 1 all the time. The theologians don't seem to talk about the philosophy of arithmetic about 1, which I think you should first know. Like the physicists do their homework. When they use mathematics, they try to figure out what's going on in Hilbert spaces and complex numbers before throwing it around. The theologians seem to me, as Frege says, think it's such a simple thing, 1. Well, Frege even said that, it's so simple. So why should we take a course on mathematics? I mean, 1, infinity maybe, and then 3, it's almost as easy, right? Just 3. But it turns out numbers themselves are actually, like people used to think this way. People make fun of Pythagoras and others for combining theology and Plato and mathematics. I think we should combine those two, done correctly. Not necessarily number mysticism and so on, like Pythagoras, but I think there is much philosophy and even theology contained, if you look at that the right way. And mathematics, as Gödel would say, has paid a price for its success. I think it's moved leftward. By sucking out all the rightward direction, it's made it, so to speak, acceptable to the zeitgeist, and he said it's been very useful in physics and so on, but it's left the other side of it entirely sort of in bad repute for the cranks like Gödel and me to play with. But I'm trying to suggest with Gödel that in fact that's a mistake. It should enjoy its rightful heritage. In fact, Gödel says mathematics has become, so to speak, the right hand of the positivists, so that mathematically inclined philosophers tend to be very leftward, materialist, etc. And Gödel was an exception to that, and I think that was very powerful. He said that there's nothing leftward about mathematics per se. In fact, on the contrary, by its nature it leans to the right. And which also explains something also very ironical, which is the physicists, the most hard-nosed physicists, use a theory in a language which has an entirely different aspect from their empirical investigations. In fact, the hardest empirical sciences, this is what the positivists themselves discovered. is that was such to be the rock in their shoe, is that we're empiricists. Damn it, but math, it's not empirical. Damn. And that's when they thought logicism was their friend. Because logicism had a way of sort of dismissing math as simply logic and simply tautologies and so on. They thought, we got it made. Then came Gödel. So the history of these is very, very interesting because Gödel was a Platonist, not an empiricist, not an empiricist, at Frege also. But the positivists thought that the move of logicism would enable them finally to discharge mathematics. Who put up, I think you put up Quine here. Quine, also a very hard-nosed empiricist, was forced to admit that there exists some mathematical objects just because you need it for science. He was dragged, kicking and screaming. But even he said, damn it, you need it. And they're not physical. So he's the kind of Platonist, a reluctant Platonist, which I think is a very strange preaching. Yeah.
I'd like to say that I think that it's clear that numbers exist in the sense that they're impervious to what we might like about them. I mean, they have properties that we can't choose. They're there. The question is, what is the nature of the existence of them? And you talked about the axioms, the truth of axioms. Well, for example, when you take Euclidean geometry, those axioms are valid for the geometry observed in our empirical observations of space. But now they can be changed or extended or adapted to other kinds of geometry. That's also a property of other structures of mathematics that can be, you start out with one idea, one empirical observation or one set of observations, and then you find out that the structure you've abstracted can be applied to other contexts. I think there's something rather remarkable in that, but go back to the question of the truth of the postulate of action.
So you raised two interesting questions, see if I can remember both. Yeah. So the first one, I would want to make a distinction, as Aquinas says.
Yes.
You say, of course numbers exist, the question is the nature of the existence. I would disagree, again, with Frege. I think existence, the question is not the nature of the existence, but their nature. In other words, they're not kinds of existence, there's just existence. There's not mathematical existence, spiritual existence, there's just existence. But for mathematical objects, something else is required to exist than for a hand, or for a planet, or for a divine being. So that's the distinction Frege makes, which I very much like. One notion of existence, different kinds of objects. So the question, if you believe in mathematical objects, is not what kind of existence, but what kind of objects are they? That's one thing. Now, your second point's a very tricky point. And so let me give you, if we have all the time, I would work on this more clearly. So, take the axioms of Euclidean geometry. Are they true? Well, if Frege is like a lawyer, he'll say, I want a yes or no question here, are they true? Now you got to be careful. If you really want just plain truths in mathematics ultimately, I think Frege does, then you've got to say that the axioms of Euclid aren't fully explicit. You've left out the parameter Euclidean space. So when you put that in, then they're absolutely true.
Yes.
So Euclid thought they were true, period.
Yes.
And that's a mistake. But also, they're not false. What you want to say is they have to be parameterized to Euclidean space, and they're absolutely true of Euclidean space. So once you do that, then you get to Frege science. And so all of math should ultimately be getting to truths which are literally true, and that if there are alternative possibilities, you haven't gotten to the actual axiom yet. So non-Euclidean space is true of axioms are true of non-Euclidean space, and then the question is which of those applies, as you say, to physical space is a good question. Frege actually is interesting. Amazingly, thought non-Euclidean geometry was simply a mistake. He thought it was consistent, but had no model. This is pre-Einstein. Actually, also post-Einstein. But he wanted just plain truth, and I agree with that. I mean, you think of your mind. So if you want truth, so for example, the Cantor postulate, this is what Frege says. This is how arithmetic differs from geometry, he says. This is how arithmetic differs from geometry. Is Euclidean axioms are true only of Euclidean space. But Cantor's postulates are true, period. And that's, he says, shows their kinship with logic. He says, try denying any of them and see where you get, he says. So Frege thought that showed, again, part of his logicism. By the way, his logicism did not extend to geometry. So logicism is that all math except geometry can be reduced to logic. But the idea that Cantor postulates cannot be denied, he thought, without falling into just contradictions, distinguishes them from the Euclidean. But I think that's the way to put it. So when you fill in the details, it's true of Euclidean space, and now it's just plain true. Good.
I had another comment that when you said that 1 plus 1 plus 1 is 3, but there's not another 1. You have a 1, you don't have another 1. This reminded me how the Egyptians worked with fractions, because they had a half, a third, a fourth, a fifth, but they couldn't imagine that there was a second fifth, nor a second tenth. So if they wanted something like 2/3, it would have to be a half plus a sixth.
Very interesting.
And so it seems there's something primitive that
Sure.
was closer to a perception of reality, as you said with Plato.
Yeah, that's very interesting. And again, I think that Egyptian idea is the idea, again, of a language versus the symbol versus what it stands for. Frege is also very good in distinguishing numeral versus number.
Yes.
Very big on that. And so when I say 3 is equal to 1 plus 1 plus 1, there are 3 numerals for 1. So that's the first. So it's definitely 3 of something, right? But they're not 3 ones, otherwise we'd be in real trouble. But people have tried that out. Serious mathematicians or serious mathematicians have, but you really want to stick to just 1, so to speak. You can actually say 1 instance of the concept 1. Okay. But there are 3 numerals. But then the question is, all those 3 numerals name a number. So if I said, I've got Paul and Paul and Paul, all I've got is Paul, right? So, but that just shows and in English is not the same as plus in arithmetic. That's what Frege shows. So you really, and that's why Frege is so interesting. He poses this sort of in a grid line, in this puzzle, like, it's the same one, but how can you get, and so he gives a philosophical explanation of the plus function, which is quite sophisticated. So it doesn't mean the same as Nixon plus Nixon plus Nixon, because that's just Nixon. So, and though again, one often says 1 and 1 and 1, that's a mistake. Plus means something distinct. It doesn't mean eating, it doesn't mean and. It means something which Frege builds in. In fact, if anything, you take one thing and another thing and another thing. That's how he explains it. And the word 1 drops out. It's got to do with quantifiers. So it's a subtle analysis. But I can see why if you didn't have Frege, you say, yeah, I can't repeat 1/5. I already used 1/5. So I'm more on 1/5. So that's funny. And again, distinction between numeral and number, to me, is just basic. But many mathematicians, even there's some famous ones who make this mistake. They've even said things like 2 can't really be 1 plus 1. Because look, 2 is 2. And how different 1 plus 1 is. Well, yeah, they're numerals. But I mean, Frege insisted that really is an identity. 2 really is. Many people want to say 2 is equivalent to 1 plus 1, it's the same size as 1 plus 1. Frege says, no, there's a number 2, and it really is, under another description, 1 plus 1. So 2 numerals and 2 senses in Frege's semantics, but 1 object named. A lot of clarifications of that. Good.
Well, I guess we can thank Palle Yourgrau for this very fascinating and wonderful lecture, and hope that mathematicians will profit from it. Thank you very much.
Thank you.